4.1, absolute maxima minima, local maxima minima, critical points, and the last one, the absolute maximum minimum, and we are going to find where is it or is it available for the function provided. So this is just the main content of 4.1, mainly target on the maximum minimum values, especially the absolute. So we're going to see the differences between the absolute and local. And some textbook, they use the term absolute as global. Okay, global. And some textbook use the term local as a relative. Okay, so don't be surprised if you check out another textbook and they use the term relative maximum instead of local max, local min. So um the absolute and the local term is it kind of is more common use in the for the contents in calculus 1, just in case you see other definition, other names, so they are the same thing. And it makes sense to me. The local means just a particular area, not the entire graph, just a certain interior point. For the global, that means for the entire graph. So look at the big picture or just a smaller picture. The absolute means for the entire thing, which means global. The relative means just a particular section. You just look at that portion of the graph. All right, let's get started with the absolute maxima minima definition. By definition, so you have to look at the interval I. Some interval, that pretty much the domain in general. Okay, if not the domain, it has to be the given interval or the interval provided. The function is a f. Okay, f at c greater than or equal to f at x for every x. So gonna be some value c. C is the x value within the interval. That value, um, that value c within the interval provided. Someone, um, yeah, missed the class, but email me anyway. Um, so the function f and the x is within the interval, some c, which is the x value within the interval, but the function at that point c is greater than all function value within the interval. And that function value is called the absolute maximum. And the other way, if that function value is smaller than anything else, it's called the absolute minimum value. For the graphical way, you could see that like, for the entire graph here, for the interval I, okay? And x would be in this interval I. For this graph, you can see that I would name it as the C1. The C1 point is the function value at C1 greater than or equal to all the function value within this interval I. Okay, that point. And also, um, if I look at this graph I just drew, at this point, that I name it as C2. So this point, the FC2 is less than or equal to all function value for this interval I. So we call C1 as a point that gives you the absolute maximum value, absolute for the entire portion, okay? And the point C2, that's a point that gives you the absolute minimum value. When you talk about the value means the Y value. The x is the point that gives you that absolute max or absolute min value. So when you read the instruction of the problem, make sure you are going to give the answer as the y value or the x value. Okay, I will point it out when we get to the example. All right, those are about the absolute max, absolute min. So the consequence of this extreme value theorem, see the name's extreme, right? Extreme value and the theorem involving the extreme value. The function that we will use, it has to be continuous on the closed interval AB. And if it satisfies these two conditions, continuous on a closed interval, this function has the absolute max and absolute min. So for example, the graph that I drew earlier, this is the continuous function. Why I know it's continuous? Because the graph is all smooth and it's all connected um, in one in one single curve here. Okay, continuous. Is that in a closed interval? Yes, in a closed interval, because I drew it within the endpoint here and this endpoint. So by the extreme value theorem, it guarantees that this graph gonna have absolute max and absolute min. Okay, that's how to explain this theorem. All right, so the next example, we're going to use the graph provided here to identify the points, if any, on the interval AB. AB, the A here, B here, right? At which the function has absolute max and absolute min. Uh, okay, absolute max, absolute min value. Then explain your answer is consistent with the extreme value theorem. To explain this part, recall the extreme value theorem. Extreme value theorem, you need the function to be continuous on the closed interval. On the closed interval. Continuous means smooth graph, right? Smooth graph. Closed interval, that means the left and the right end are defined very clear, or the graph is defined based on what you see here. So based on the extreme value theorem, number one, f is continuous. Number two, there's a closed interval. Okay, closed interval AB. Okay, as you see here, the closed interval AB, the continuous. If you have these two as a property of the graph provided, so the theorem guarantees that you're gonna have absolute max, absolute min. And what you have to do after that, you have to identify what point that give you the absolute max, what point give you the absolute min. Okay, like this example, let me adjust it real quick. For this problem, you have the graph like y equals f of x, and it looks like it's continuous, right? Continuous. Does it meet the condition? Number one is continuous because the graph is smooth in one single piece. Yes. Number two is that in a closed interval. Yes. A, B. Yes. So check. All right. And let's see if we can identify the absolute max, absolute min. So the problem asks you to find absolute max value at at x. So we're gonna look at the x that provide the absolute max. So from the graph, you just see like for the entire graph, where is the highest location, the highest right here, right, right there. So at x equals b. That's the answer. The at x equals b. If it asks for the value gonna be the function at b. Value is a function at b. Next, for the absolute minimum value, minimum, the lowest of the graph, that is at C2, x equals C2, will give you the absolute minimum or the lowest of the entire graph within the interval AB. And the value is the function at C2. That's how you answer it. The problem might ask you to put the value as the answer or put the x as the answer. So read the problem carefully, how the form of the answer has to be put in. Okay? Questions? It's straightforward. No computation yet for the earlier part of this section. Okay, no question. Nothing on the chat. So keep going. All right, next one. The graph is provided, but the graph has two pieces. Well, that's not a good sign, right? So let's check the conditions of the extreme value theorem. Number one, is the function continuous? It's,
No.
it's not continuous because we see the broken point right there. Okay, if it's not continuous. So the answer is no for the last piece here. So it doesn't meet the condition. If it doesn't meet, the extreme value theorem does not guarantee that you're going to have absolute max, absolute min. You might have it, depends on individual graph that you have, in a problem. But by the extreme value theorem, it doesn't it is not sure that you're going to have it or not, so it's uncertain, so it depends case by case. So the answer for this is no, it doesn't meet the condition, and we have to find out directly from the graph. And from the graph, even though it has the closed interval, right, from A to B, but we have to look at the highest point of the graph. It looks like this is the highest, supposed to be at x equals d, right? X equals d dot. What is the function value at d though? Does it have the function value at d? Hmm? What is the function value at d? The function value at d is y1 because it's defined right there, right? It's defined, or it's a solid dot. The function value at d, but from the graph, it looks like it's the highest is at d as well. But the thing is, if it do get closer and closer to d, the function value is not defined right there, close to the d from the left, but it's defined right at d equals y1. Okay, supposed to get the maximum right here, but since you cannot tell what the value gonna be, even though it gets closer and closer to the y2, so um the function, I mean the maximum value doesn't exist for this case. The absolute maximum value at x is gonna be none, because you cannot name any number that is the highest value of all. Okay, none. Even though we can find the function value, but at that point, the function value is not the maximum overall. Okay. And the second case, the second one here, for the absolute minimum value for the entire graph, this is the lowest. And we can name the function value at that point. So at x equals a, give you the absolute minimum value, and that value is the function at a. Okay, so another reason we can say this: f at d equals y1 is defined, but not the absolute maximum value, because it's not the greatest value overall. Okay, when we talk about the absolute, that means for the entire domain or entire given interval. Question number two. So this will go along with the extreme value theorem, that it doesn't guarantee that you're gonna have it. You might find one of them, or you might find both of them, but is not the concrete way to say, okay, you're gonna have both. You might or you might not, or you might have just one or two. Okay. Another example. This is another smooth graph, so that's a good sign. Let's check off the conditions of the extreme value theorem. Number one, yes, the function is very clear, it's continuous because it's all in one piece. Okay, all in one piece. You don't have to lift your pen or pencil up and down. So number two, now what we're gonna do, we're gonna check, okay, is that in the closed interval? Yes, we can see the left and the right end at point A and point B. So we have the closed interval. Yes. Yes, with the extreme value theorem conditions, we know that we're gonna have the absolute maximum, absolute minimum. Okay, yes. And then let's find out, let's confirm from the graph. The maximum, that's the highest value. The minimum is the lowest overall for the entire graph. For this problem, at x equals r, right? X equals r will give you the value or the absolute maximum value as a function at r. And for the minimum one, the lowest is at x equals u. So the value would be f at u.